Hi everyone, welcome back. We are going to work through some problems now for this chapter. It's a lot of problems to really understand what's going on here with all these reactions. It's sort of a mess, right? So what I encourage you to do is work out the problems I have here. These are from an older edition. Let me walk through what problems they are. This one up here is 21.73. This one is 21.77. So instead of doing problems out of the book, I've just put some of them in here already for you. So these are the ones that I'd like you to work out for homework. Okay, these ones. And then this one down here is 2176 part B, 2176 part C. This one is 21.88. And this is in the 3rd edition Klein. Okay, so I'd love for you guys to try these first, and then this video is to help walk you through it if you're having trouble. All right, so try to do it on your own and come back when you want to go through the answers. All right, so here we are with the first one, and what I'm looking at is highlighting the things that are changing. So notice that we've got this group being added on. That's sort of a new thing. So I like to show that. So this carbon group here is this carbon group here. And so what I need to do is get a molecule of this in here. So what I'm going to do is probably add this molecule, which is an ester, ethyl acetate, and I need to have this alpha hydrogen removed, so I'm going to add a base, and I usually match it up with the ester. So it's an ethyl acetate, so I use ethyl I'm going to use ethoxide. Okay, so that's my base that's going to grab this hydrogen, make the enolate, and then attack here. And this is going to come back down and kick out that group. So that's how I get this beta keto ester. This is the Claisen condensation, if you don't remember that. Claisen, go back and look at that. So that's step 1. Okay, in the next step, I need to cleave this off. And I remember there's a decarboxylation reaction. So in the next step, what I'm going to do is I need to cleave this group off. So if I can convert this to CO2 using acid and then heat, this will come off as CO2. Okay, and then I'll have this group remaining here. All right, so that's step 2, and that's decarboxylation. For the third reaction, I need to add another carbon on here. So I've got this kind of thing going on. And to add a 1 carbon unit, and I notice there's unsaturation here, it's probably a condensation, and it's an aldol condensation. How do I know that? I know this double bond might have come from an OH group. A beta hydroxy ketone or aldehyde can be made using aldol by adding however many carbon unit you need in terms of an aldehyde or ketone. I need a 1 carbon unit to be added, so I'm going to use formaldehyde. And then you'll see how it makes this a beta hydroxy ketone. And then in order to eliminate that, I'm going to do this under basic conditions, so NaOH is fine, and heat will help me eliminate it and get this unsaturation here. So that's my 3rd step. And my 4th step is to add to that even further. I'm going to add 2 carbons to that. So whatever I have here, add 2 more carbons. And this is going to be a Michael type addition. I think I want to add a nucleophile here. This is my electrophilic carbon. Because of resonance, it pulls electrons away. So I need a nucleophile to attack here. So I need a soft nucleophile. I don't want to use Greenyard. That's too hard. It'll attack the nucleophile. Let's use a organolithium cuprate. Okay, so I'm going to use CuLi with 2 R groups, and the R groups have to be ethyl. So Et2CuLi, and that's going to give me an enolate. So the ethyl group will attack here, and that'll give me this enolate. And then I need to work that up with water. So I'll probably have step 5 as a water step. All right, and then after that, and maybe a little bit of acid, dilute acid just to get it back in the keto form. And then after that, I need to add on this last piece here, which is another 1 carbon unit. And of course, I could do that the same way I added on a 1 carbon unit up here. I could use formaldehyde. And of course, this has no alpha hydrogens to pull off, so my nucleophile has to be over here. So, oops, my nucleophile is the alpha carbon right here. So this will get formed after NaOH, and then this will attack here, and I'll do my beta hydroxy group, which then gets eliminated if I have heat. Then I'll get a double bond there instead of an OH group. Okay. All right, so that's a lot of stuff here. Claisen, aldol, Michael addition using Gilman reagent, and then another aldol. All right, so that's good review. Let's see if you guys can see what kind of syntheses we could do here. Or actually, before this problem, let's go to here. This breaks it down a little bit more, so I like that. So this first problem is, how does this react with acid and heat? So I think this one, we want to focus in on the fact that these are esters. These are ethyl esters here. So it's C double bond O, O, E, T. Okay, those are all esters right here. And we know that through acid that there's, these get protonated and then water comes in and it replaces these ethoxy groups. So I'm going to end up with carboxylic acids in here, 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 and here. 4 carboxylic acids. Then with heat, we know that because they have access to these carbonyl groups, that these could get decarboxylated, and these could get decarboxylated. So I'm going to end up with, let's see, 6 carbons, so that means all of these left as CO2. So I'm going to end up with this carbon skeleton, and these carbonyl groups remain, but the rest have been released as carbon dioxide. I'm going to double check 2, 4, 6, 8 hydrogens and 2 oxygens. So hopefully you remember that as up here, decarboxylation, convert it to carboxylic acid. When you have a carbonyl next to it in the beta position, so here's alpha and beta to this carbonyl, that means this carbonyl is susceptible to be lost as CO2 through this kind of a mechanism. Okay, so I'm going to make CO2 and lose that group. That's called decarboxylation. All right, in this next step, I have an ester here again and here as well. So a strong base like ethoxide here, it's going to remove a beta hydrogen and make an enolate here. And then notice I can do an attack. If it helps, I would write out these ester groups. So maybe rewriting this as this might be more helpful to you. Okay, so I would definitely encourage that. And now, when this becomes an enolate, it can attack here, and we can close up that ring. Okay, so and then we're gonna push these up, we're gonna push those down, and we're gonna kick this out. So that's how we make a beta keto ester. So let's show that. It's gonna look like this. This is gonna be sticking out. This is sticking out. 1, 2, 3, 4, 5. It's a 5-membered ring, and this group here is like that. And this group here has an ester still attached. Alright, so when I draw this, I have to be sort of careful here. I'm going to draw this like that. I draw this. I know this attacks their carbonyl here. Then I have another carbon, and then I have this. Then I have my ester, original ester here, and then it attacked here. All right, and let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons, and 3 oxygens. Everything looks fine. We're doing an acid workup here, but I didn't hydrolyze it, so it must be dilute acid. Now with acid and heat, that's going to convert this to carboxylic acid, but then it's going to decarboxylate. So once that decarboxylates, it's sort of like chopping that all off. Okay, so that's going to be what I have left is this, and that is C8H12O. All right. For the next one, I have alpha bromination, but it's in acidic conditions, which means it's going to be on the more substituted side because it goes through an enol, and the enol that's thermodynamically more stable is on this side. I'm going to get monobromination. So that one's going to be a Br here. That's the structure there. And let's double check. 1, 2, 3, 4, 5 carbons, 9 hydrogens, Br, and an O. Okay, so this structure is this one right here. And then with pyridine, that's a non-nucleophilic base. And what that's going to do is notice the bromine's going to be eliminated, so along with the hydrogen. So it looks like it's going to do an elimination. So probably we'll get elimination like this. So one of these hydrogens, it doesn't matter which one, is going to get attacked, and this do like an E2 kind of reaction. So I get this. After this, 1, 2, 3, 4, and then another carbon, 5. Okay, and I'm making sure that's right. Now I'm going to do Gilman reagent. So that's already telling me, oh yeah, that makes sense. I'm going to have an ethyl group attack here. And then I'm going to tautomerize this and get my ketone back. So this compound here should look like this. I've got this, like that, methyl group, and then I have an ethyl group that added on. And then you can count that up. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Oh yeah, and then a methyl iodide. Right, I need to add that on as well. So here I'm going to have, okay, so instead of tautomerization, it's good for you guys to learn, right? So it's going to go like that. And then after this next step, I'm going to attack the methyl iodide. And then that's going to add another methyl group to the alpha position. So my final product is going to look like this. Like I had this before, and then I added the methyl iodide. So the enolate neutralizes itself through this attack, so I don't need to have a water workup here. All right, so now 1, 2, 3, 4, 5, 6, 7, 8. Good. And my last one is LDA, which is makes the kinetic enolate over on this other side over here. Then that's going to attack ethyl iodide. So my compound here is going to have methyl on this side and ethyl on that side. Okay, so it's sort of nice when it chops it down into small pieces, and now you can do like really big stuff like this or this over here. Efficient synthesis for this, you can notice it's going to be intramolecular. So I'm going to need to figure out if I use an enolate either here or here, it doesn't matter which one. I'm going to then use that to attack the carbonyl carbon at another site. Then this will come back down and kick that out. So let's count this. This is 1, 2, 3, 4, 5, 6. That's how I get a 6-membered ring here. And then what happens after that is I should still have an ethoxy group. I should still have this ester there, right? So this ester should be hanging off of carbon 1. And so it looks like I got rid of it. So that means that I must have done a decarboxylation here. So that is after the first step. And sorry, I have to write over this. This is running out of room. Okay, so after the first step, notice carbon 1 attacked carbon 2, and carbon 2 became a ketone. Carbon 3, 4, 5, 6, I'll just go around the ring, 1, 2, 3, 4, 5, 6, and carbon 1 had an ester group on it. So it sort of looks like this after this first step. I have a beta keto ester after Claisen. When I want to chop off a group, I need to maybe do decarboxylation, right? So to do decarboxylation, I need to do acid and heat. So before I get too far into this, step one was I need a base to come in and do this intramolecular Claisen reaction. So NaOET is enough to do that. Step two is I need to decarboxylate this. So I'm going to turn the ester into a carboxylic acid and then do heat to get rid of that as CO2. Step three is I need to do the methyls at the alpha positions. So maybe I will do one equivalent of NaOH, and step four might be methyl iodide, and then maybe step five might be LDA, just to make sure that I get the enolate on the other side, and then you do methyl iodide again. So actually what I have in the answer key is that in order to prevent NaOH from coming in and just doing multiple alkylations, might be better just to do LDA and do this step, and then do LDA again, and then do this step again. That way you avoid, with LDA it's pretty bulky, so you're not going to come in and do another deprotonation because it's bulky. So yeah, I would probably do it this way. All right, for the next one, I'm looking at, wow, this is crazy, isn't it? Okay, so we've got at least this top part accounted for in this molecule here, and then what I need to do is add carbons to it. So if I had something like this, maybe like this, and another one like that, then these alpha positions could be deprotonated and attack here, and then I could do sort of an aldol condensation to get these pi bonds. So I would want this compound with NaOH and heat, so that will be aldol. In this one, I'm looking at how this carbon skeleton, 1, 2, 3, 4, 1, 2, 3, 4. Okay, so if those match up, then I'm really looking for a way to add this 3 carbon unit to here. So I just need a way that this can be a nucleophile to attack here, and then maybe this comes off. Well, one way we could do that is if we had an alpha carbon that was an enolate, and this is my electrophile. So maybe I would add acetone and NaOH, and then have this sort of mixed Claisen, or aldol, I mean, mixed aldol. So this would come in, and, oh, actually this would be Claisen, this is leaving. And then I would end up with maybe something like this. But the problem with that is I have 2 carbonyls, and it's hard to get rid of one of them. So that's not going to work. So what I really need is some kind of a carbon nucleophile. So how do I make this carbon nucleophilic? There's a couple of things you could do. One is I could try Greenyard, but Greenyard tends to react twice because you make a ketone and then it reacts again. So one thing I might try is maybe another one like it. So OET, like that, 1, 2, 3, 4. And this could attack here. And then we would end up with beta keto ester. So what would that look like? It would look like this molecule, except 1, 2, 3, 4. Except here we would have the original ester. And then what we have, so then we have 1, 2, 3, 4. One of these attacks one of these, the ester group leaves, but then we want to get rid of this group. So then we know how to do that, right? So we have sodium methoxide, and then I don't have to draw this again. I can just assume that 2 of these will react if I put sodium methoxide in. So first reaction, sodium methoxide, do the Claisen condensation. And then second reaction is I need to do that decarboxylation reaction. So step 2 will be the acid and heat. And then that's how this group cleaves off. Okay, And then the last one here in this problem is I notice a cleavage here. So I start with this molecule and I need to add a bond here. And this looks like a 1, 2, 3, 4, 5 away. So if you remember, this is one where we could do a Michael addition. So the compound I'll need is NaOH to get an alpha enolate. And step 2 is I'll have this. And, and then step 3, I could do water workup or dilute acid. All right, sorry about that. My laptop just died, so I rebooted up. So anyway, here we're doing a Michael addition. And the thing is, though, we talked about Michael donors and Michael acceptors. This is a good Michael acceptor. That means it's a good electrophile for the Michael addition. But this is not a great nucleophile. This is a little bit harder nucleophile than if it had 2 carbonyl groups. So one thing that we learned in this chapter was to make that into a softer nucleophile for the Michael addition. We want to maybe change this into an enamine, and that would make this reaction even better. So this is okay, and it might work, but something that would increase the yield for this could be to make this into an enamine first. So we add a secondary amine. So step 1, maybe an alternate method would be step 1, dimethylamine. And what that does is that makes this into an enamine, like this. Oops, other way. Too many bonds on that side, right? There's the enamine. And then this nitrogen has a lone pair that would come down, attack here, and we make the enolate that way. And then that's how the addition works. And notice we're using this instead of NaOH. So we would just add we'd make the enamine by using these reagents, and then I'd add this alpha beta unsaturated enone, okay, 2-but-3-one, okay, but 3-ene-2-one is the name of that, by the way. And then we'd add the water just to neutralize it at the end. And again, if you want to do dilute acid workup, that's fine too. Just water or dilute acid just to tautomerize it back to the keto form. Okay, for each of these problems, it used to be in 22.89, now it's 21.78 in the newer 3rd edition. We're starting with cyclohexanone, which is this compound. So we really need to alpha alkylate here. What compound do I need to do that? So reagents I need to go from cyclohexanone to this ethyl cyclohexanone would be maybe NaOH or LDA, some kind of base to create an enolate here. And then I need an ethyl, maybe ethyl halide, something like that. Okay, for part B here, now I want a beta alkylation. So here, wow, so that's tricky, right? I can't just pull off an alpha hydrogen. I need this to be some kind of reactive site. And remember, this comes from maybe something like this, where this carbon is now electrophilic. Okay, so I'm thinking a Michael addition where I have organolithium cuprate of some kind. So the organic group would be an ethyl. So ethyl lithium cuprate. And it's a Gilman reagent. And this would be my nucleophile that attacks the cyclohexenone. How do I make the cyclohexenone? Okay, so one way that you could do that is by doing an alpha bromination using acid and bromine, like we talked about earlier in the chapter. You can do an elimination then using a base of some kind to it's like an E2 elimination right there. If you can use a bulky base, but you don't have to use a small base also. This hydrogen is the most acidic hydrogen because of the conjugation you get as a product. Then you have the ethyl group come in and attack. You do your Michael addition. And then at this stage, if you wanted to alpha alkylate it, you could. But you could just, if you're happy with just the beta alkylation, you could just add water, dilute acid to neutralize it. So maybe just some dilute acid to neutralize it and have the enol tautomerize back to the keto form. Okay, I think in the next problem you'll see that we can alpha alkylate it as well. Just by at this stage, instead of adding water and doing the workup, we can instead use methyl bromide and get a methyl group here. And that problem would be for part C. We do the beta and the alpha alkylation using the Michael addition. And we had to make the Michael the Michael acceptor first. We had to do that by having a BR here and losing it. All right. For part D, starting with cyclohexanone, which is this molecule, you could see I'm adding this group onto it. Now for this, you notice it's going to be another Michael addition, where this was the nucleophile, so this is my donor, and it's attacking here. This must have been some kind of electrophilic carbon, like a double bond, right? And that's electrophilic because of resonance. So this attacks here, but remember, this is not a great Michael donor. Michael donors are softer nucleophiles, just like we were talking about up here. You may want to convert it to the enamine first, and then do the Michael addition and tautomerize it back to the keto form. So for this problem, we were talking about maybe converting it to some kind of enamine using H plus and methylamine, dimethylamine. So that's step one. And then we could do a Michael addition with the compound that we need here. Okay, so I think you guys can see the mechanism like that. And then once we have this, we will want to hydrolyze this back off. So you could do that with water and acid, where water will attack here, and this will get released after many proton transfers. This will get released again. You'll have a carbonyl here. And then here you'll have the enol that in acid tautomerizes to the ketone. So at that stage, you'll get the product. So H3O plus in water, H3O plus, which is acid in water. All right, so 3 steps here. The next one to me looks like an aldol. I'll tell you why. We got maybe cut through these alpha beta unsaturated bonds, and you see how this is probably an enolate that at one point attacked here. This became an OH group, and the OH group got lost in a condensation. And then we repeated it for the other side. So writing that one out, I get NaOH attacking benzaldehyde, makes this aldol product, which then can get, with condensation or heat, can lose water and make the alpha beta unsaturation. And then step 2, you could do that again, okay, just to get it on the other side. Or perhaps you could write excess at the beginning, and then it might occur on both sites. This next one, I would probably write it out. This CO2ET means C double bond OOET. Okay, so it's an ester. And notice it's 1, 2, 3, 4, 5 away. So we're talking about another Michael addition. Probably the Michael acceptor is going to be this alpha beta unsaturated compound. And so I will want to attack from an enolate here to here. But make a note that this is only a 1 carbonyl. It's not really a soft nucleophile. An enolate is softer than like a Grignard for sure, but it would be softer if it was an enamine. So why don't I do the enamine here, and then that will be a really good Michael donor, and then this will be my Michael acceptor. Okay, so just writing it out, I would end up with, all right, so I would end up with this enamine that then, all right, I'd end up with this enamine that then attacks this Michael acceptor. I'd end up with this sort of, it looks like looks weird because of the ethoxy group here, but it would be kind of enolate ion here, and then this imine. To neutralize that, I would have acid and water. That would attack here and eventually hydrolyze that. So eventually I'll get this, and then this side over here will get neutralized and then convert back to its keto form. So on this side I would end up with the ester. Now this mechanism here, you might have forgotten it already, I don't know. When you have H3O plus, you basically have water in solution to attack here, and then this part gets protonated and it leaves, and the water oxygen can come down and become a double bond. I'll just do that real quick just to jog your memory. Okay, so without drawing the rest of this, if you guys recall, we do some proton transfers, right? So I'm going to neutralize this by putting the proton over here. Now this is a good leaving group, so I'm going to bring this down. And that's how I get my carbonyl group here, and that's how I hydrolyze away the amine. So it's the reverse of this first step, basically, okay? Or acidically, I should say, right? Okay, it's a bad joke. But anyway, this comes down, then I can neutralize that later. Okay. All right, so that is how this imine turns into a carbonyl group, is through that hydrolysis from chapter 19 with your aldehyde ketone reactions. And this is just enol keto tautomerization here. And then our last one is pretty simple, just NaOH to get an enolate on either side of cyclohexanone. So we start with this, we do NaOH, we get this, and then we do methyl iodide or whatever halide you want to use, and we get that. And then on the second one, you have to be careful because you don't want it on the same carbon. So you do have a choice of how to make that, how to control that reaction, okay? And that's through kinetic or thermodynamic control. So after the first one, because it doesn't really matter what you use for the first one, you'll get one alkylation. And then you just want to make sure you don't add the second one here. You want it on the other side. So what base do you want to use? Do you want to use a small base or a bulky base to deprotonate over here? Hopefully you know you need a bulky base. So LDA is bulky, it'll come over here. And then I'll do my alkylation over there. So I'll just do another one. Okay, so that's how we do that one. Like that. Okay, if I wanted the dimethyl group over here, I would use a small base, and it will have that be the major product because that's a thermodynamically more stable enolate when it's more substituted on that side. All right, last question here on this page is how do we do a synthesis for this reaction? Going from a 5-membered ring to a 6-membered ring, and it looks sort of complicated, right? So, you know, there are some reactions in the past, like from first quarter OChem, where we had ring openings and things, like carbocation shifts that can do a ring expansion, kind of like. But you know, this kind of problem makes me think that we need to open it up and then close it up again, but close it in a different way. And part of why I know that is because this carbonyl group looks like it comes from some kind of oxidative cleavage here. So if let's do oxidative cleavage, we'll get carbonyl groups here. Now there's two kinds of oxidative cleavages we could do. We could do under reductive conditions like ozonolysis, where you get aldehyde here and a ketone here. Or you could do under oxidizing conditions, you could make this a carboxylic acid. Okay, so let's look at doing both. Okay, so if we look at doing both here, notice that when you open this up, if I used ozone and DMF or zinc as a workup, O3 to zinc and water, that will give me the aldehyde. If I want to do this under oxidizing conditions, I can use Jones reagent or KMNO4 heat and H3O plus workup. Okay, so either way, let's see what happens. Okay, if I want to close this back up into a 6-membered ring, then how do I need to do it? First, notice I like to number these just because I think it's easier, you know, to keep track of. And then I need to think of a way to close this into a 6-membered ring. So maybe if I had this enolate attack here, okay, that could be possible. And maybe it would prefer to do that instead of here, attack here, because that will be a smaller ring. 1, 2, 3, 4, right? 1, 2, 3, 4-membered ring. Here it'd be a 1, 2, 3, 4, 5, 6-membered ring. Okay, so that's going to be more likely to occur. Also, the aldehyde's more reactive as an electrophile than the ketone is, so that's another thing. All right, so you guys can see with my numbering. Let's see, this is carbon 2. Let's say this is carbon 1, 2, 3, 4, 5, 6. So at carbon 6, I should have a hydroxyl group here. All right, now if I'm trying to go from here to here, maybe I will have this turn into a alpha beta unsaturated by doing an aldol condensation. So maybe this was a NaOH, and this is heat to do an aldol condensation. Now I have a Michael acceptor, and I just want to do an alkylation here. So I could do CH3, I could do this organolithium cuprate, so Gilman reagent, and I can go there. All right, so that could be my, let's see, step 1, ozanolysis. Step 2, under reductive conditions, gives me the aldehyde. Step 3, NaOH to do an intramolecular aldol with heat. So I would put those together. So NaOH and heat, aldol condensation, which gets me to here. And then step 4 would be the Michael addition. So this attacks here. And then maybe I do an acid workup, dilute acid workup, just to get the enol to the keto form. Okay, so that's one possibility. Another possibility is you could do the oxidative cleavage to here. The problem is with NaOH, it'll take this hydrogen instead of doing an enolate, because this is way more acidic. So something you can do is you could change that into an ester. So we could do H plus ETOH. Or you could do Socal and ethanol as well. Okay, SOCl2 and ethanol as a follow-up. Once we have this, you can see we could probably do Claisen condensation. And then instead of an aldol with an OH here, we'd end up with a beta keto ester. So, or we'd end up with a beta keto group. So instead, right here, instead of the OH, it'll be this ketone. At this stage, a compound like this can be difficult to work with because we can't distinguish one ketone from the other, so they're basically both going to react. I can't protect one over the other because they're both reactive. They're the same reactivity. There are things I could do here. Maybe I could like alkylate at the alpha position, but other than that, really can't figure out a way for that alkyl group to be beta to any one of these, and then a way for me to get rid of that keto group. Now, in my answer key, I sort of show how we get this compound, and maybe it's possible if you had some kind of reaction that maybe you had like a methyl Grignard, MEMGBR. Maybe you could react one here. Like I said, it's probably likely it'll react at both places. Even if you specify one equivalent, you might have some molecules where there's 2 additions anyway, but it's not ideal anyway, but it's possible. Okay, so let's just follow that through. So you'd have this, and then at this point, you could try to do condensation or some kind of elimination, like maybe acid and heat to get rid of that OH group. I'd prefer to be this way rather than the other way because it's conjugated here. And then once you have that, then we can just get rid of that double bond by doing a hydrogenation, H2 of PT. So this method is sort of long, and this is a little bit problematic here, just because it's difficult to control without having it alkylate at both places. You could try with saying one equivalent, but you'll still get alkylation in both places potentially. So for those reasons, it's probably better just to go with the aldol route.